Good morning, friends. Time to start the class. So what did we do in the last class? We stated this specific theorem called the Schroeder-Bernstein theorem. And what does the theorem statement say? The theorem statement says the following, right? So if you have A and B, which are sets, if there is an injection, let's say F from A to B, and there is also an injection, let's say G from B to A, then actually there exists a bijection between A and B. Right, so this theorem is trivial when A and B are finite sets, right? If one of them is infinite, then the if itself is going to be false, so the theorem is true, right? So the only interesting case is where A and B are infinite sets. And in the last class, we also saw a high-level idea of how do you prove this, right? So what was the idea? So let's quickly recap it, and then let's write down the formal proof. Right, so how does the idea work? So let's say you have the set A, you have the set B, right? So suppose this is the injective function F, right? Right, so what stops me from saying that F is actually a bijection? The reason is that there could be some elements in B which don't have a pre-image under F, right? In fact, there could be, I don't know, infinitely many elements of B which don't have a pre-image under F. So how do you take care of them? So you use G to take care of them, right? So what do we do? What do we do? So look at this element. Let's say this, let's call this B, right? So it does not have a pre-image under F. So we use G. So let us look at what is G of B. Okay, so G of B is going to be something. Let's say this element, right? So what we'll do in our bijection is we'll actually say, okay, look, because B does not have a pre-image under F, right? So in our bijection, B will be paired up with G of B. Now, what is the problem? Since we are trying to construct a bijection, this guy, so this guy's partner is lost. What will this person do? It will again apply G and find its partner, and so on. Okay. Raise your hand if this high level idea is not clear. We are going to now write the formal proof. Okay, you start out with F, and then everybody on the right hand side who has a problem applies G to themselves and then pairs up with that person. Okay, so that might land. So somebody else might land up in a problem. So they again apply G and pair up with that person. Okay, so that is the idea. So this is the function F and this is the function G. Okay, so let us formally write down the proof. Right. So let us define the set of these elements which have a problem over here, right? Let us define this set as B. Right. So let us define this set as B prime. So what is B prime going to contain? B prime is going to contain all elements which don't have a pre-image under F. And it is also going to contain all those elements which are reachable from these elements via applications of G and F. Okay, so G applied, then F is applied, then G is applied, then F is applied. So even this person will be in B prime. Okay, so let us define B prime, right? So define. Okay, so first of all, this is proved by construction, right? We are trying to prove there exists an injection. So there exists a bijection by construction, right? So let's define the set B prime. Let B prime be the set of all B in capital B such that what? Such that first of all there should exist, right? So there should exist some starting point which is not in the image of F. So there exists, for which there exists some B star not in the image of F, and so there should exist a finite length path in some sense, right? So what is the formal way of writing it? And there should exist a K in N union 0 such that such that what? So if you apply G and F alternately K times to B star, you should get B. Such that what are you applying? You are first applying G, then applying F, then applying G, and so on. So you are applying F compose G, applied K times to B star is equal to B. Okay, and similarly we'll define let A prime, right? So A prime are the points in A which appear on this path. So A prime is simply the set of all G of B such that B is in B prime, right? So all these will appear in A prime in this case. Any questions up to this point?
So why can't K be infinite?
Why can't K be infinite? What do you mean? What do you mean infinite K? What do you mean by infinitely many applications of F and G?
Like they're infinite sets, so it can go on.
So just understand the difference between boundedness and unboundedness and infiniteness. So here I'm not restricting K to be at most 100. Right? All I'm saying is there exists a natural number.
Okay. Okay.
Okay. Yeah. Yeah. So what do you mean by infinite applications of a function? That's not clear, no?
Yes.
Okay. Yeah. Good. So now what? So now define H going from A to B as H of A is equal to F of A if A is not in A prime, and otherwise it is equal to G inverse of A if A is in A prime. Right? So remember, if A is in A prime, then by definition there must exist some B such that G of B is equal to A. And moreover, because G is an injection, there must exist a unique such B. Right? So therefore, so note that G prime A, G inverse of A is well defined due to definition of A prime and the fact that G is injective. Okay, so therefore this is a well-defined function. This is a function in the first place. Now what is our job? Our job is to prove that H actually is a bijection. Okay, so we claim that H is a bijection. Right, so before we prove this claim, let's first understand these sets A and B. Right, so let's take the definitions on the next slide. All right. So now observe. Right. So what do you want to observe? So first observation is that for all A in capital A, what do we have? So right, the following are equivalent. What statements are equivalent? Statement number A is this element A is actually in capital A prime. Statement number B is right. So G inverse of A exists and is in B prime. right? And C, f of A is also in B prime. Okay, so I hope this is easy to check. If A is in A prime, then by definition A is G of B for some B in B prime, right? So G inverse of A exists and it is in B prime. This is straightforward. If A is in A prime, then okay, yeah. So okay, so maybe this requires some work. So if A is in A prime, if A is in A prime, then what is f of A? So A is G of B for some B in B prime, right? So f of A is going to be in this case. So right. So should we prove? So how many of you can easily prove this? Raise your hand if you think you can easily prove this claim.
Sir, like the first part I'm not getting, like for all A belong to A belongs to A prime.
No. I'm saying the following are equivalent. What does this mean? I mean,
Oh,
if any
okay.
one of them is true, then all three are true.
Okay, got it. Thank you.
Okay, so each one of them implies the other. That's all I'm saying. Okay, so not many people are able to prove this on their own. So let's do this. Let's do this. Fine. Right. So, what is the proof of A part implies B part? So this follows from the definition, right? So follows from definition. Right. So next, let's maybe yeah, what do we prove? Let's try to prove A implies C. Right. So A is in A prime. So therefore, G inverse of A. Right. So A is in A prime. A is in the set A prime. So therefore, G inverse of A. I mean, yeah. Okay. Actually, sorry. So what we are really proving is B implies C, which is kind of fine. Let's prove B implies C. Right. So G inverse of A exists and is in B prime. So therefore, what? So f of A is equal to f of G inverse A, right? Or okay, actually let's not make it too complicated. Let's say let B is equal to G inverse of A. So then f of A is equal to sorry, f of G of B, right? So this is equal to f compose G of B, right? But now we know that we know B is in B prime, right? So therefore there exists some, again by definition of B prime, there exists some B star not in image of F and K such that F compose G applied K times to B star is equal to B, right? So that is just by definition of the set B prime. So now what do we have? So now FA. So now FA is just F compose G applied to B once again. So that is FA is just F compose G applied K plus 1 times to B star. Yeah, so therefore FA is in B prime. And what? So now what are we left to prove? C implies A, no? If we prove C implies A, then we are done. Then we have proved that all the three statements are equivalent. So how do we prove C implies A? If A is in B prime, okay. Yeah. So FA is in B prime, right? Okay. So C implies A. FA is in B prime. This is given to us, right? But right. So let's say, okay, let FA is equal to B for this specific proof, or maybe let's call this FA equal to B prime. Let's say, suppose FA is B prime, and we know B prime is in capital B prime, right? So now what? Now what? So we want to prove that A is in capital A prime. Okay. So now, yeah. So what does this mean? What does this mean? So this means that B prime is not in, sorry, this means that B prime is in image of F. Okay. So, but because since B prime is in capital B prime, there exists some, yeah, you apply the definition of B prime. There exists some B star not in image of F, right? And K such that F compose G applied K times to B star is equal to this B prime. Okay, but now what? So B prime is in image of F. Okay, why am I not able to write? What is the matter? Achha, okay. Okay, so B prime is in the image of F, but B star is not in the image of F. So now we have B prime cannot be equal to B star. So therefore your K must be greater than 1. K must be greater than or equal to 1. Right? Because yeah, so if K is 0, then if F compose G is just the identity function. Right? So now what do you do? So now you consider F compose G applied K minus 1 times to B star. Right? So F compose G applied K times to B star is B prime, and out of that the last application of F is so it's really taking A to B prime. Right? So therefore A is equal to F compose G applied K minus 1 to B star, and then you are applying G to this. Right? So this we know is in B prime by definition. Right? And therefore A is in prime. Okay, I think there is something on chat. Divyanshu, image of F and B prime won't be disjoint, need not be disjoint. You're right. You're right. Right. So if you observe what we had on the last slide, right? So this element, for example, was in the image of F, but it was still in B prime. Okay, good. So now more property. So this yeah. Yeah, somebody saying.
So could you explain the last step again? Could you explain the
last
last step again? Now B dash not equal to B star.
This entire C implies a part or something else?
No, sir. The last is it consider this belongs to B dash. A equals to this.
So did you understand that B prime cannot be equal to B star?
Yes, sir.
And K must be greater than or equal to 1. It cannot be 0. Is that, I mean, what is F compose G applied 0 times to an element? It's just that element itself, no?
It's just the same element, right?
Yeah, so, which is why K is greater than 1. So which is why I'm considering this element. F compose G applied K minus 1 times to B star. And by definition, it is in B prime.
Okay, okay, sir. Got it.
Okay. And now, in fact, A is just G applied to this element. Why? Because if you apply G and then apply F, you get back B prime. And whereas F of A is B prime. So here you're using injectivity of F effectively. Okay. So now what? Yeah. Okay, cool. So now the other observation. Okay, so let's add a page. Okay, so observe. Okay, so let's not say this is an observe, this is a claim. Claim. Right. So similarly, we can make a claim about every element in the set B. So claim. Right. So for every B in B prime, sorry, every B in capital B, the following are equivalent. Okay, what is equivalent? First of all, right? So we are making corresponding claim. B is in B prime. Second statement. Okay, so if F inverse of B exists, then it is in A prime, right? So I'm not, so observe the difference here. I said G inverse of A exists and it is in B prime. So here I'm saying F inverse of B exists. If F inverse of B exists, then it must be in A prime. Okay, and C, right? So correspondingly, F of A is in B prime. So here I'll say that G of B is in A prime. Right, so the proof is more or less going to follow the same path. Okay, so should I leave it to you? Okay, so raise your hand if you're not confident that you will be able to prove this with a little bit of effort. Right, so the proof is going to follow more or less the same path. Okay, cool. So people are confident about it. Good. So now let us make the claim that, right? So proof left as exercise. Okay, or maybe I'll include it in the tutorial sheet. Okay, so now I want to claim that H is injective. Right. So what was the definition of H? Let us recall. Um, right. So this was the definition of H. Right. So I want to claim that H is injective. Why is H injective? Right. So let us name these claims maybe. So let's call this claim 1, and this claim 2. Okay. So why is H injective? Right. So it's a matter of, yeah, Divyanshu.
Yes, sir. In the definition of F, in definition of H, I think so. In one of the case, it would be A belongs to A. In both
Oh,
cases.
yeah. Sorry. So here it is A does not belong to A prime, and here it is A belongs to A prime. Right? A prime is a subset of A. Is this okay now?
Yeah. Okay.
Did I make this mistake earlier? Oh, I made that mistake earlier. Yeah. Okay, so why is H injective? So suppose F of A, sorry, H of A is equal to H of A prime is equal to some B, let's say. Okay, so now we need to prove that A is equal to A prime. So if case 1, if B is in B prime, what do we have? So we have that, right? So if B is in B prime, then what do we have? So then G of B is in A prime by claim 2. Right. So now what? Right. And okay. So moreover, what? Yeah. Moreover, sorry, I should have said this earlier. Right. So G inverse A exists and is in B prime. Okay. So where should we start with then? Acha, so maybe this is the wrong point to start. Sorry. sorry. So let's make cases on where these A and B, A and A prime lie, right? So if A and A prime are both not in A, then what do we have? So then H of A is equal to F of A, H of A prime is equal to F of A prime, right? So because F of A is equal to, so therefore what do we have? So therefore F of A is equal to F of A prime, and therefore A is equal to A prime, right? Because F is injective, right? So similarly, case 2, if both A and A prime are in A prime, then what? So then H of A is equal to G inverse of A, H of A prime is equal to G inverse of A prime, right? But G inverse of A and G inverse of A prime are the same. So therefore, by definition, A and A prime must be the same, right? So G inverse of A is equal to G inverse of A prime, right? But G is a function, right? So therefore, A is equal to A prime. And finally, case 3, right? So now what? So if A is not in A prime and A prime is in A prime, right? So what do we argue? What can we argue in this case? Right. So A is not in A prime, right? So therefore, H of A is equal to F of A, right? So A is not in A prime, so F of A is not in B prime, right? Because all these three conditions are equivalent. A is not in A prime, so therefore F of A is not in B prime, right? So this is not in B prime, right? And this is by claim 1, right? So now, but what do we have? So A prime is in capital A prime, so therefore A prime is in capital A prime. So G inverse of A, right? So exists and it is in B prime. So now what? So right. So therefore H of A prime, which is equal to G inverse of A prime, right? So this is in B prime. So this is again by claim 1, right? So therefore contradiction. Right, so we said H of A is equal to H of A prime, but here we said H of A is not in B prime, and here we said H of A prime is in B prime, so they cannot be equal. Okay, any questions so far? Right, so what are we left to prove? We are only left to prove that H is surjective, and then we are done. Okay, so let's try to prove that H is surjective.
Sir,
Yeah,
so when we said that this is a contradiction to case 3, right?
this is a contradiction to the assumption that H of A is equal to H of B. Sorry, H of A is equal to H of A prime. Okay.
Okay, हाँ ठीक है.
Yeah. Okay, so let us actually copy this on the next slide. Okay, so the claim now is that H is surjective. Right, so for every B in the set capital B, we want a pre-image under H. Okay, proof. Does somebody want to tell the proof? Does somebody want to try out using the definition of B prime and A prime? Right, so maybe let us also copy this on that slide. So Okay, Ramanuj.
Yeah, sir. So the proof I think is as simple as if if something exists in B prime, then it can be reached through H via A belongs to A prime, and then if it doesn't exist in B prime, then by definition it has a image in, because all of the B stars which didn't have an image from F, which existed like in A, so they.
I don't understand what exists and what doesn't exist.
You defined the
Can
B
you make
star.
it more concrete?
So there was this B star which didn't have an image in F. So all of those which
just
didn't
make
have
it
an
formal. Hold on. So just make it formal. How do you make it formal? You want to prove. Okay, my pen is somehow not responding. This is so weird. Acha, okay, good. So now what do you want to prove? When you say that H is surjective, you want to find a pre-image for every B, right? So consider an arbitrary.
We can say a B, and then we can take two cases in which B belongs to B prime and which B doesn't belong to B prime.
Very good, very good, very good. So case one, which one do you want to tell first?
I guess B doesn't belong to B prime.
Then what?
Then by definition of B is not one of the B star. So therefore, an image exists.
Correct. So B prime has a pre-image. So therefore what? So F inverse of B exists, and what?
And F inverse of B exists, and that is for some F of A, and we can say H of that A is equals to B.
Why? So you want to say that so if inverse B exists and it must be in A, it must not be in A prime, right?
F inverse of B is not in A prime. Also by
it's not in A prime. Very good, right? So F inverse B exists and is not in A prime, right? So why is this? So this is by claim 2. Right, so what is claim 2 saying? If B is in B prime, it's saying the following three are equivalent. If B is in B prime, then right, so if F inverse B exists, then it is in A prime. So now we have that B is not in B prime. So what is the not of this statement? The not of this statement is F inverse B exists and it is not in A prime. Right, so the not of P implies Q is P and negation Q. Right, so this it can also be written as F inverse B doesn't exist or it is in A prime. Right, so but now B is not in B prime, so F inverse B exists and it is not in A prime, right? So therefore what? So therefore H of F inverse B is equal to F of F inverse B, which is equal to B. And case 2, somebody else? Somebody other than Ramanuj? B is in B prime. Then what? Arin?
Yes, so sir, if B is in B prime, wait, yeah. If B is in B prime, then yes, sir. Then G of B exists.
This is helpful, no?
Yes, sir.
Sorry?
Yeah, would be. If B is in B prime, then G of B exists, and it means G of B is in A prime.
Is in A prime. G of B always exists. Yes, good. That is the proof.
Yes, sir.
Right? So
G of B is in A prime. Then we have a pre-image of B in as in A. That is
good. Very good. Very nice. Yeah. So therefore, G of B is in A prime. So again, this is by claim 2. Right. So now because G of B is in A prime, so what is H of G of B? H of G of B is simply G inverse of G of B. So this is equal to B. Right. So let us quickly, I mean, this was a long proof, so let us quickly go through it once again. How did we, how did we write this proof? We first said that, okay, why is F not a bijection? F is not a bijection because there could be several elements of B which don't have a pre-image under F. So how do we fix those? So we said that, okay, let's try to tweak F into a bijection. How? So for everything that does not have a pre-image, like, right? So let's just under H, let's just make G of that element to be the pre-image of that element. But then that will leave, because H has to be a bijection, that will leave somebody else unhappy in the set B, right? So they can again apply the function G and get their partners, right? So that is going to cause some more breakups. Okay, and then this will go on, but the formal way of writing is, so this B prime, right? So B prime is the set of all B's who are going to cause breakups. Okay, which is same as the, yeah, so this same as the set of all elements B for which there exists some B star not in the image of F, and some finite case such that if you apply F compose G, right? So G F G F G F K many times, you apply to B star, then you get B. And similarly, so A prime is the set of all people in A who are going to be a part of this chain of breakups. Okay, good. And then we defined H as follows. Then we defined H of A to be F of A if little a is not affected by a breakup, and it is going to be a G inverse of A if little a is affected by a breakup. And then we claimed that H is a bijection, right? So for which we proved two critical properties, right? So if so when one says one talks about the implications or the equivalences between equivalence between the statement A is in A prime, and then what happens to F of A, what happens to G inverse of A. And similarly, we had an equivalence between B in B prime and appropriate statements which talk about the F inverse of B and G of B. Right, and using these two claims, we proved that first that H is injective, and then we proved that H is surjective. So that way, therefore H is a bijection. Bijection from A to B. Okay, so raise your hand if something is not clear so far. Okay, cool. So people seem to be with me up to this point. Awesome. Okay, so now what do we have? So now coming back to the original question, which I stated in the last class, how can we say that some set is of the same size as that of the as other set, or some set is larger in size than some other set, or smaller in size than some other set? Right. So this was an intuitive notion which we did not define. Now we are going to define it. Okay, so define it in a way that it kind of agrees with the intuition that we have. Okay, so for finite sets, it was damn easy. Just find the size and then compare those two numbers. But for infinite sets, that's not going to happen. So now the immediate question is, a question we'll try to answer after this is, are all infinite sets kind of equivalent? Do they always have the same size? Right, so we'll come to that, but before that, we'll define this notion of cardinality. So we say we say that the cardinality of set A is, okay, so I'm making three statements in one statement over here, is at most equal to at least the cardinality of set B if there exists there exists what? Right. So when do we say that the set cardinality of set A is at most the cardinality of set B? We say that when there exists an injection.
A to B.
Yeah, very good. Injection from A to B, bijection between A and sorry, I should have changed the color, no? Bijection from A to B, and third case, an injection, or rather I can say a bijection between A and B. Why not? Why do we say bijection from A to B? Between A and B, let's say. A and B, and then in the third case you want that there exists an injection from B to A. Okay, so this is the way we will compare the sizes of infinite sets in particular. For finite cases, or when one of the two cases is finite, other is infinite, the answer is obvious and it agrees with this notion. Okay, so note that when these sets are non-empty, I mean, let's not worry about the corner case where the sets are empty and so on. So when the sets are not empty, this is same as saying there exists a surjection from B to A, and this is same as saying there exists an injection. Sorry, there exists a surjection from A to B. Right, so we have seen that. So if A and B are in non-empty sets, then there is a surjection from one set to the other set, if and only if there exists an injection from the other set to the first set. Okay, is this fine? So now one more little definition. So we say a set A is countable if its cardinality is at most the cardinality of the set of natural numbers. Okay, so or equivalently we could have said that, or equivalently, what are two other equivalent ways of saying the same thing? Using injections and bijections or whatever. Right, so basically these two, no? At most the cardinality of set B. So A, the set of cardinality of set A is at most the cardinality of the set of natural numbers. So what is the two equivalents? What are the two equivalent conditions? So or equivalently there exists an injection, or equivalently there exists an injection from A to N. So other equivalent statements are this is the first equivalent statement. Second equivalent statement is A is either empty. A is either empty, or there exists a surjection from N to A. Right, so these are the other two ways of saying. Yeah, Aradhya?
So can we say that the cardinality of the set of natural numbers is the smallest among the cardinality of all infinite sets?
Smallest among the cardinality of all infinite sets, yes, you can say.
Okay.
Yeah. So why? Because if a set is infinite, then you can then it is non-empty, obviously. So you can pick out one element right? But even if you pick out one element, there are still infinitely many elements left. So you can pick out one more element, the second element, right? So if a set is infinite, you can always say this is the first element, this is the second element, this is the third element of the set. There could be more elements which are left, but then this gives a injection from the set of natural numbers to that set. Okay, so Aradhya's comment is Aradhya's claim is that every the cardinality of any infinite set is at least the cardinality of n, right? So if you want, you can just give this a little bit of thought on how do you write this proof. Okay, and maybe we could discuss this in the tutorials. Okay, so take this as a tutorial problem. Okay, so now what? So look at this condition. A is countable. A is defined to be countable if either A is empty set, right? So that's the trivial case, or if A is not empty, then there exists a surjection from the set of natural numbers to the set A, right? So this is same as saying that A is equal to some A1, A2, A3, and so on. Right, so you can list down the elements of A, right? List down all the elements of A without missing any element. Okay. Any questions so far? Okay, good. So now, obviously, all finite sets are countable, right? So we are more interested in infinite countable sets, or which are also called countably infinite sets. Okay, so can somebody give me more examples of countably infinite sets?
Set of odd number.
Sorry?
The sets of odd numbers, all odd number.
All odd numbers, yes, that is clearly infinite and that is countable. Why? Because you can give you can give an injection from the set of okay, what way do you need to give an injection? There exists an injection from A to N. Yeah, obviously every infinite set of the set of natural numbers is going to be countably infinite. That is clear. Shrimanti, any set that is not a subset of natural numbers but still countably infinite? Shrimanti, yes.
Set of rational numbers.
Rational numbers. Okay, good. But good, fine.
Negative integers. Negative integers.
Negative integers. You can just say the set of all integers. Okay.
Sir, the set of reciprocal of naturals.
Yeah. So basically, if you apply a bijection from, or if you apply a 1-1 function to the set of natural numbers, which goes into some set of real numbers, let's say its image is going to be countably infinite. Good. Yeah, fine. So okay, so let's try to make these claims. So claim, right? So somebody said set of rational numbers is countable, but even before handling rational numbers, let's just worry about the set of integers. So Z, right? So Z is clearly infinite, but the claim that we are going to make is Z is countable. Right, so does somebody want to give a proof? Right, so remember the condition. So to prove something is countable, you need to show an injection from that set to N, or a surjection from N to that set. Yeah, Shrimanti, do you want to tell it?
Yes, sir. We could say that Z minus and Z plus, and include 0 separately. So z minus would be minus n for all natural numbers, and z plus would be n for all natural numbers, and 0 separately. Then we have
No,
it
but
countable.
what? No, I don't understand. I want an injective function from the set of integers to the set of natural numbers. Note that the set of integers is a strict superset of the set of natural numbers. But
Yes,
still, I
sir.
want to construct an injective function. What is the inductive function? What is
Yes,
the
sir.
injective function?
I am saying that, sir, suppose we define f from z to n such that it is minus n when z is negative, and it is plus n when z is positive, and 0
So
when z is 0.
Okay, let's say f of n is minus n if n is less than 0 and it is equal to n otherwise. Is that fine?
Yes, sir.
Is this acceptable? What did we want? We wanted an injective function from z to n. Is this an injective function?
So
Right,
like we can,
Srimati, yeah.
we can say that
So it could be surjective from n to z, not
so
injective.
surjective from okay, fine. So you can try that, but let's give a chance to somebody else. Prabal. Prabal,
Sir,
yes.
Sir, I was thinking about a proof by construction.
Yeah, sure.
So basically, we can map the a1 to 0, and then suppose I'll start with a pattern and then we can follow it. Sir, so a1 is 0, and then a2 is 1, and a3 is minus 1. Then a4
I
is
see. So you are actually giving a bijection between n and z, right?
Yes, sir.
Okay. So the pattern he's trying to follow is the following. So right. So this is the number line, which is a valid thing. So this is a1, then 1 is a2, then minus 1 is a3, this is a4, and so on in both directions. Acceptable. Vedant, did you have some different idea?
No, sir, I was going to say the same thing.
Okay, so anybody else, Ananya or Ramanuj, did you have something else?
So you can just define this as a function. So
yeah, exactly. How do you define it? How do you cleanly define it as a function? There is something on chat. Let's see. F of n. Okay, so Tanmay has said something. Let's see what Tanmay has said. So Tanmay says that let us define f of n is equal to 2n if it's minus 2n if n is less than 0, and otherwise it is 2n plus 1 otherwise. Sounds good. Yes, Tanmay, very nice. Yeah, so now okay, Vedant and Ramanuj, your hands are still up. Did you want to say something?
No, sir, done.
Okay, good. Okay, so now raise your hand if you are not able to prove that this f is actually a bijection, right? So we claim that f is a bijection between z and n, or bijection between z and n. Yeah, good. So raise your hand if you think you are not able to verify that f is a bijection. Okay, good. So apparently everybody is able to verify. Good. So somebody said the set of rational numbers is countable. Somebody claimed that, but before that, let's do something else, right? So before that, let us actually claim that. Oh, by the way, so now since we are kind of making the collection of countable, we are adding more and more countable sets to our sort of vocabulary, right? So there are other ways to prove countability, right? So let's get to them, and then we'll prove more sets to be countable. Okay, so observe that if f and g are both okay, so if f going from a set A to B and g going from the set B to C are both then F compose G is right. So I hope you can all verify this easily. So now if I want to prove some set is countable, what do I, right? So suppose we want to prove that some set A is countable. Right, so what do we really need to prove? By definition, we just want an injective function from A to N, right? So we want an injection. But then due to these properties, right? So we know that every countable set has an injection from itself to N, right? So instead of this, instead we can prove, right? So instead of getting directly an injection from A to the set of natural numbers, sometimes it might actually be easier to get an injection from A to some other countable set. A, so B, where B is known to be countable. Right, and then you show that there exists an injection. Shrimanti, yes?
Sir, equivalently, like we could also show that there's a surjection from N to A. With that be accepted also.
Exactly, sure. Although you'll have to just worry about the corner case where A is empty set, but in most cases that's kind of obvious.
Okay.
Okay. Right. So similarly, as Shrimanti said, you could actually want to you could want to prove that there exists a surjection from N to A, but instead of that, you could actually prove that there exists a surjection from some set which is known to be countable to A. That is also good enough. Okay. Yeah. So is this idea clear? Okay. Cool. So now what? Now let us prove something else. Let us add more sets into our vocabulary of countable sets. Right, so let us prove okay, let us prove that N cross N is or countable. Yeah. Any idea how do you prove this is countable? Okay, first of all, raise your hand if you don't believe that N cross N is countable. Okay, so everybody seems to believe that N cross N is countable. So any idea of the proof? Right, so let us get back to how did we prove that Z is countable, right? So one of the earlier proofs was that, okay, this is 0, you call this the first element of the set. This 1, you call this the second element of the set. This 2 minus 1, you call it the third element of the set, and so on in both directions. Yeah, okay, good. Divyanshu?
So like if there's an element of N cross N, say A comma B, so like we may map it to 2 to the power A, 3 to the power B, something like that.
Sorry, you map it to what?
2 to the power A multiplied by 3 to the power B.
3 to the power B. Awesome. Very nice. Very nice. Very nice. So you are good. So this will give an injective function from N cross N to N. Yeah, this sounds good to me. Somil?
we can first order the elements of n cross n based on their sum, and for two elements which have the same sum we order them based on the first component, like 1 comma.
I see. So you're trying to say if so this guy, let's say so this guy is actually 1 1, but what I'll say is this is my A1, this is my A2, this is my A3, right? So A4, let me draw bigger. Okay. So Somil's idea seems to be that this is my A1, A2, A3, A5, A6, and so on, right? So A7 appears over here. Is this your idea, Somil?
Yes.
A9, A10, and so on. Yeah, but this is also a good idea. 2 to the power a times 3 to the power b. So let us maybe just take this as our proof. That's kind of easy. Okay, so yeah, proof. We construct an injection from n cross n to n. Right. So what is the injection? So define H. Define H going from n cross n to n as H of m comma n is 2 to the power m times 3 to the power n. Yeah, Chinmay?
Sir, I also had some idea, but it is more complicated. Like I was mapping a comma b to the ath power of the bth prime number.
That is fine. Sure, that is fine. That is fine. Right. So Chinmay's idea is h of mn is what?
Like
so
mth power of nth prime number.
Nth prime number to the power m. That sounds good. Yeah. So this is the other possible way, right? But this what I don't know who, I forgot the name. I'm sorry. So this idea actually gives a bijection between ends. So this is a bijection between n cross n and n. Right?
So what was this idea? Can you repeat once?
Sorry?
What was this idea, the bijection?
Oh yeah, the idea is the following. Yeah, so look at this grid, right? So what he said was right. So look at this grid of n cross n, right? So this is number 1 comma 1. This is 2 comma 1, 1 comma 2, and so on, right? So what he said was, let's draw these diagonals, right? So this diagonal, then this diagonal, then this diagonal. Okay, right? And then he said that this is the first element of our set. Then look at the next diagonal. This is the second element, third element. Look at the next diagonal, fourth, fifth, sixth. Look at the next diagonal, 7th, 8th, 9th, 10th, and so on. Right? So every mn which is in n cross n is going to appear on some diagonal, and therefore it will be assigned some number. And this will be assigned in a 1-1 on 2 way. That was the idea. Ramanuj?
So you can easily give this a function. So mn, so you define m plus n equals to some c. So you do c minus 1 by 2 my plus m or something like that, and that will give a unique number.
Good. Okay, sounds good. So for now, let's just take this maybe as a little exercise, right? So define this formally. So define this bijection formally. Exercise. define this bijection formula. Okay. Cool. So now what about the set Z cross Z? Can I easily prove that that set is also a countable set? Aniruddha?
Just go in a spiral. So here we kind of went in a zigzag.
I
So
get it. Yeah, you're right. Yeah, so let me just go to the next slide, write down the claim, and then yeah, I'll write down your proof idea. Yes, you have the right idea, Aniruddha. Claim Z cross Z is countable. And Aniruddha's idea is look at Z cross Z. Right, suppose this is your 0, 0. This is your origin. Then Aniruddha's idea is this, I'll call this as my first element, A2, A3, A4, 5, 6, 7, 8, 9, 10, and so on. So he's going round and round around the origin like a spiral. Sounds good. That is actually, so this is actually a bijection between Z cross Z and N directly. But now can we actually use the fact that N cross N is countable to get a much simpler proof of Z cross Z being countable?
So like we can just, for every Z cross Z, we can like map it to a N cross N.
Exactly how?
Like we can just take modulus, like map it to N cross N with 0, 0. So we can just take the modulus,
I think you have the right idea. You are making it explicit, but I don't need to, right? So proof, right? So we give an injection from Z cross Z to N cross N. Right, so remember this diagram. As soon as you give an injection from a given set to another set which is known to be countable, you actually prove that A is countable. Right, so we know that N cross N is already countable. We already know that N cross N is countable, so it's enough to give such an injection. So how do we give such an injection? So we know that Z is countable, right? So let H going from Z to N be an injection. Okay, so define, right? So this injection exists because Z is countable. Exists because Z countable. Right, so now how do we define an injection from Z cross Z to N cross N using H? Yeah, Divyansh.
A plus K, we can map it in Z. If we have a positive K, we can map it to 2K in N, and for a negative K, we can map it to like 2K plus 1. And so
well, one sec. So this is okay. I'm assuming that there exists such an injection. So I'm assuming that you have constructed this injection. I want, using H, I want to construct an injection, define H prime going from Z cross Z to N cross N as what, and I want this H prime to be an injection. What is the easiest way of doing it?
Like if the first element is odd, we like positive K in Z, then we can map it to 2K in N for the first element. Like we can apply that 2 times now from, if we can map it from Z.
Aren't you making it more complicated? Divyanshu, what idea do you have?
Like we can map H dash M comma N to HM comma HN, right?
Absolutely. Right, simple. I mean, you just apply that injection coordinate wise. That's all. Okay. Divyansh, anything else?
Yeah, I get. Sorry.
Okay, fine. Right. So this is an injection. This is an injection. Right. So Z cross Z is countable. Awesome. Cool. Now let us ask the question: why is the set of rational numbers countable? Right. So claim Q, the set of rational numbers, is countable. Any ideas? How do you prove this?
Sir, Q is a subset of Z cross Z.
It's not a subset of Z cross Z, but then yeah, there is a natural way to associate Q with a subset of Z cross Z. Yes.
Yes, sir.
Q is technically not a subset, but I get your idea. So could you just tell the proof?
Sir, we can write any rational number in P by Q form.
First of all,
P and Q are
plan. Hold on. So you are giving first give the plan. So you want to give. So we give an injection from Q to what?
I think we can use the fact that
Right
Z
idea.
cross Z
Where
is
is that
countable.
injection? Sorry?
We can use that Z cross Z is countable like directly.
Good. Z cross Z is known to be countable, so you give an injection from Q to Z cross Z. So what is the injection? So define H as H going from Q to Z cross Z as follows. How do you define?
We can take any arbitrary rational number P by Q, where P and Q are we can say that they are co-prime.
Okay.
And we can map it to P comma Q.
Okay, good. Yeah, awesome. Sounds good. So you are saying that okay, you want to map H of P over Q, or rather, H of R is equal to P Q, where PQ is the unique pair such that R is equal to P over Q and GCD of P and Q is 1. Is this enough? Is this enough, or do you need to add something else to this? Is PQ the unique pair? Okay. Is there always a unique pair for a given rational number? Is there a unique pair PQ such that R is P over Q and GCD of PQ is 1? So I claim that there is a slight inaccuracy over here. Yeah.
Yes, sir. 2 by 3 can be also written as minus 2 upon minus 3. Are you seeing that?
So how should we fix this? How should we fix this?
We can.
Q is always positive.
Exactly. Vaibhav, you're right. Yes. And Q and 0. Very good.
So we could do this by we give an injection from Q to N cross N.
You give an injection from Q to N cross N. How?
Same cheese, same thing.
But then P could be negative, no? So there is some more work is involved. So yeah, so you'll have to apply your Z to N injection on the P part, right?
Okay. Yes.
Yeah, but yes, that is possible. Nothing wrong in that. Cool. Right, so Q is the set of rational numbers is countable. Okay. Z cross Z we proved to be countable. So I hope you can okay. Yes.
What if P is 0?
What if P is 0? So this is question to whom? I don't understand. There is no problem if P is 0, no?
Then GCD would not be 1, na? Then GCD would be Q. Then we can only take. P by 0 by 1.
Acha. Oh, I see. That's what you're saying. Hold on. So if P is the okay, so let's fix this. So this is if R is not equal to 0, where P is the unique pair such that, and otherwise you want to define something, no? Otherwise we'll just define H of R is equal to 0. Otherwise, right? So that is if R is equal to 0. So is this okay?
Yes, sir.
So what was the problem initially? Like 0 would have been mapped to 0, 1.
0 would have been mapped to 0, 1. Yeah. What is the issue with that?
Sir, but it could also be mapped to 0, 2. So it would.
No, but we want
has
GCD.
one.
We want the GCD to be 1. We want the GCD to be 1. We want the GCD to be 1. So you cannot map it to 0, 2. Then the GCD would be 2. Right? So
You
I
can
don't
only map to 0, 1 and 0, minus 1.
No, because you want Q to be greater than 0.
Okay. Sorry. Yes.
Yeah. Okay. So I don't see a problem with this. Let's just get rid of this. Okay. Cool. So now I'll leave the following as exercises for you to figure out in the tutorial sheet. Right. So, but let me just mention them now. So prove that. Claim if so if A and B are countable sets, then A union B is countable, and part 2, A Cartesian product B is countable. Right, so these are going to into the tutorial. Right, so I'll add all of these problems that I've mentioned today in the tutorial sheet, and then I'll share it once again with you by tonight. Okay, so just try writing a formal proof of this. So now I want to make a slightly more ambitious claim. So here A union B is countable, good, but I want to slightly make a more ambitious claim. So I want to say the following. Right, so these are in the tutorial. So the next claim that I'm going to make is the following. Let A1, A2, A3, and so on. So I'm taking infinitely many sets, countably infinitely many sets. Right? Why are they countably infinitely many? So the number of sets is countable, right? So the collection of sets is countable, right? So this is the first set in the collection, second set, third set, and so on, right? So let this thing be a countable collection of sets each of which is countable. Right, so the collection itself is countable. How many sets do I have in the collection? Countably many. Okay, could be finite, could be infinite. Rather the more interesting case is where these are infinite, and each AI is also a countable set. Then the union over I going from 1 to infinity of these AIs, right? So which is another way of writing A1 union, A2 union, right? Okay, so let me say countably infinite collection, right? So interesting cases where this is countably infinite collection. Okay, so this is same as A1 union, A2 union, blah blah blah, right? So this is infinite union, right? So this is also countable.
So isn't this just equivalent to saying that n cross n is countable?
Almost, yes, you're right. Almost. Yeah, very good. Very good. Right. So here is the mental, exactly. Yeah. So that is the idea. So here the mental picture you should have is the following, right? So this is a set of natural numbers, right? You have 1, 2, 3, and so on. So this is, so think of the x-axis as this countable collection of sets, and think of the y-axis as enumerating the sets. Okay. So what I'll do on the y-axis is the following. So remember these sets are countable, right? So I can imagine that the first element of the first set is written over here, right? So A11, A12, A13, right? So I am enumerating the first set A1 on this first line. I am enumerating the second set A2 on the second line. The third set A3 on this third line, and so on. Yeah. So that is the idea. Okay. So except possibly that you need to just worry about, or this thought should come into your mind that possibly these AIs are overlapping. Right, so we could possibly have A13 equal to A34 or whatever. But that's not really a problem. Why? Because you are just trying to construct a, let's say, a surjective function from n cross n to the set, to this set. Okay, so proof, we will, so if, okay, so if this union, if all AIs are empty, then union I going from 1 to infinity is equal to the empty set, and therefore it is countable. Corner case, let's get rid of it. Okay, so otherwise we construct a surjection from, look at the direction, n cross n to this set, union over I going from 1 to infinity. You can construct an injection from this union to n cross n. That is slightly, I mean, it's going to be slightly more wordy. That's all. Ramanuj?
Yes, sir. So I was thinking, can you also do A1 cross A2 cross A3 dot dot dot? But I think that will only work for a finite number of sets, and infinite won't be countable, maybe.
Yeah, so that's for the next class. What you said is right, but we'll discuss this in the next class. Okay. Right, so we want to construct a surjection. Yeah.
Sir, if we prove the first claim that if A, B are countable, then sets, then A union B is countable, then we can use this to prove the next statement. Let A1, A2, A3 dot 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 1.
Okay, so any objections against that? Any objections against this comment? So I don't know who was it. I don't know. Somebody said that if assuming this claim, you can actually prove this claim. Yeah, Ramanuj.
So that you can use induction to prove a finite number of sets, but not an infinite number.
Exactly. So if you take this claim and you try to use mathematical induction, it will tell you that the union of some, for every n, the union of n countable sets is countable. Right?
Okay.
It will not say that this infinite union is countable. There's a difference.
No, sir, I was saying that, sir, wait, if A1 union A2 union A3 dot dot AN, where n is infinite.
What is n infinite? N is a natural number, no? Right?
We are taking infinite numbers of union, na?
Okay, so if you want to think of n as infinite, induction will allow you to prove a statement only for finite n. It will not allow you to prove a statement for infinite n.
Okay.
Right? What does induction say? If Pn is Pn plus 1, then the statement is true only for the set of natural numbers.
Okay,
right?
But
so
sir, I am not using induction actually.
Then what?
Sir, if A1 union A2 dot dot infinite times, we will first do A1 union A2. We will not doing that n minus 1. We will do A1 union A2 because A1 is countably infinite, A2 is countably infinite. Then it will produce a countable infinite set. Then we will again use that new set with A3. Like that we go on.
But then you will never get to this infinite union, no? Right? So
okay,
think
you are
of
saying
this.
that we will not end anywhere like that because it is infinite.
My point is the following. So here is a counter example. Suppose A1 is just the set 1, A2 is just the set 2, and so on, right? So now if you take the union of I going from 1 through n, ai, this is just the set 1 through n. But the infinite union, I going from 1 to infinity ai, is the whole set of natural numbers.
Yes, yes.
Yeah?
Sir, I think...
Yeah.
Sir, excuse me.
Yeah, got it.
Sir, I think what Manthan is saying can be used, sir, because we know that the set A1, A2, A3, so on, is countably infinite set. And since it's a countably infinite set, we can draw a bijection. Yes, sir. Actually, yeah, we can draw a bijection from that set to natural numbers.
Okay, so are you telling the proof or are you still trying to use induction on the first claim?
So I'm trying to use induction on the first.
Okay, hold on. So yeah, okay, fine. Will you be able to tell in the next 2 minutes?
Yes, sir, definitely.
Okay, go on. Yes.
So what I'm saying is, if we can use induction on the first claim, as we can only use induction on the set of natural numbers, but we have this set A1, A2, A3 as a bijection. Will be a bijection. There exists a bijection from this set to the natural numbers.
Fine.
So
Okay.
I think induction can be used. That's what I'm saying.
See. Induction. Okay. So induction. If you use induction on this, what you will get is that. So by induction, you will get that if. Okay, you will get that for every n in capital N, if A1 through AN are countable sets, then their union is countable.
Yes, sir. I will get this.
Okay, so do you understand what is the problem?
Yes, so what I'm saying, there would be a problem if this set R A1, A2, A3 set would not be countable. It would be uncountably infinite. But since it's countably,
hold on, that has nothing to do with the countability of AIs. Okay, so it is just the limitation of the principle of mathematical induction.
Okay.
Right. So this union that you are able to see over here, that potentially cannot be written as the union of some countable collection of these sets. Some finite collection of these sets. That is the problem. Okay. So okay, fine. So we are out of time. So let's do this and let's finish this off in the next class.
So I had one request. Can you, in the next class, can you produce an example where like such a property holds for this, like A union B, like something happens for finite elements, but would not happen when it goes to infinite? Can you produce an example?
Yes. So that will happen for Cartesian product. The Cartesian product of an infinite collection or countably infinite collection of countable sets need not be countable. We'll do that in the next class. Okay.
Okay.
All right. Chalo. Yeah. Time is up. Chalo. Lecture khatam. Bye bye.